this topic, we look very closely at the situation where we have two charged plates. There's a plate, and there's a plate there. And they will have an electric field between them. And of course, we're going to imagine a nice uniform field. So in this topic, and in this topic, that one's no good. We look at this situation many times. That's meant to be a uniform field. I know I haven't got them equidistant really, but more parallel. That's terrible. Okay. So there's this could be a positive plate, and this could be a negative plate. And we have a uniform field inside, as we've talked about in the past. Uniform field. Of course, imagine it's infinite, or that we're not taking into account the ends there. If I place a proton in here, I just put a proton in, I inject it from the side here, say, okay, inject a proton, or rather, most often in physics, it's a stream of protons. What's going to happen very quickly? It's going to go towards the negative plate, isn't it? Yeah, it's going to be repelled by the positive plate, or you can think of it like it's attracted by the negative plate. Okay, so we're going to see very quickly. Now, is there any force? Is there any force horizontally? No. We know that F equals EQ. So it's related to the force that the charge experiences is related to the direction of this electric field. It's going to accelerate toward the negative plate. So this is a positive proton. If I place the proton here, injected it down here, what will happen to it? It'll just stay there, won't it? What if I say, okay, no, I'm actually going to force it to move up towards the positive plate? Yeah, imagine if I gave it a kick or hit it with something, and with a very tiny boot, I kicked it with a very tiny boot, and forced it to accelerate up here. Of course, it would reach some point. It might even reach the positive plate before it turns around and comes back down, or it might just go up here and then come back down. I have to do work on that. That kick is work, isn't it? Work equals what? Force times distance, doesn't it? Force times displacement, or some people like W equals FD. Okay. This polarity, so the polarity between the plates, we call delta V, or potential difference. You've all heard this. Potential difference between the plates. Delta V between the plates. Oh. So the potential difference between the plates is defined as the work done per unit charge. It's a small positive test charge when it is moved between 2 points. Mathematically, delta V equals W per unit charge, work per unit charge. Can you see the units here? Yes. Joules per kilo. Or, I forgot this, volt. One, you might remember from year 11 that the work is equal to a change in kinetic energy, which is equal to the change in potential energy for a closed system, of course. Electric potential energy. Does anybody want to have a go at what they think this might be? Volts? Okay, so times charge. Yeah, okay, that might be closer. So it's, what is potential energy? Gravitational potential energy. How do you define gravitational potential energy? MGH, yes. Okay, mathematically you can say that. But what is it? It's the energy that some mass has, some object has by virtue of its position in the gravitational field, isn't it? What's that? Yes, with where it is in the field. Just the same, electric potential energy is the energy that a particle has, a charged particle has, by virtue of its position in an electric field. Okay? Well, we're just going to say potential energy delta V equals the potential energy per charge. Charge has due to its position in an electric field. Oh, we might leave this until next time, I think.